basic naming of organic molecules with mostly just carbon, hydrogen, or the halogens, whether they're all straight chain or branched. But there is a whole group of atoms that you can find that are part of organic molecules that are not carbon, hydrogen, or a halogen. So we're not going to name them specifically. We're really just going to name what the group type is. And so we'll go through a couple of molecules where you're just picking out what these structures are. So they're typically, if they're a functional group, they're either going to be, like they might be like double bonds or triple bonds between carbons and what their names are, or a ring structure of carbons, or they might be oxygen containing or nitrogen containing, or there's only one group that is a sulfur containing molecule. Okay, so if you see a nitrogen, oxygen, or a sulfur, then those can be the functional groups. So ones that you can find, there's a chart in your book that sort of shows you these functional groups and then just puts it with it what they listed as like an R. So you might see something that looks like ROH. Okay, so when you look at the periodic table, you're like, there is no such thing as an R. So R just means any organic molecule, but then has this OH group on it. Or you might see an R with a dash and H2. Okay, so that's just saying any organic molecule when you see this nitrogen attached. So the R is like the rest of the molecule, or it's just kind of like a generic way of showing something. There are so many different ways that you might see these atoms. So we're just going to go through this list and look. And they said they fixed it. I think we fixed it. I don't think we did. Okay, so I'm not a huge fan of this chart because it is so small. So I'm skipping these, but these are the ones that are in your book. Okay, so these are in your e-text. It's like table. I was looking to see if I could figure out what the table is. It's in section 4.3, the functional groups. So here's the ones that they are. So we'll just sort of list them or describe them just a little bit. So the first ones are, if you see a double bond, that's an alkene. Okay, so if you see a double bond in a molecule, then that's an alkene. So remember when they're all single bonds, those are alkanes, right? Like we had methane, ethane, propane, they all end in ane. If there's a double bond, then that is an alkene. If there's a triple bond, that is an alkyne. So I gave you, did everybody grab one of these when I came in? Okay, so this you will have on your exam. Okay, so if you look, you see that they're actually, these groups are listed on this as well. So this is kind of like your functional group page or handout. So you get this when you take your exam. I have this posted in Moodle as well. So if you like wanted to look at it or print it out or download it, it's in, I've got to move it into the exam 3 module. But you see in the upper right corner, upper left corner, you have alkanes, all single bonds, alkenes with the double bond, alkynes have a triple bond. And I will tell you, these alkenes are kind of reactive. Alkynes are very reactive. But can you see it here in this molecule? There's a triple bond. There's actually another one. These are toxins. I don't know if you remember, like the poison dart frogs that live in South America. They're the very brightly colored frogs that nothing messes with. And that's because they secrete this toxin. It's a neurotoxin. It causes paralysis. This histrionicotoxin actually causes muscle paralysis. So that is why animals don't mess with these brightly colored frogs. It's because they secrete this toxin onto their skin. So that's a pretty safe way of being able to survive through life. And they actually use a similar toxin as a paralytic agent in medicine. And that's like how they realized, or how they actually was discovered, is because they found it as a natural substance, and then drug companies like take it and then manufacture like an artificial or a man-made form of it to be able to use it beneficially, hopefully. Okay, So we have alkanes, all single bonds, alkenes have a double bond, alkynes have a triple bond. But then if you have a 6-membered ring, remember that would make it a cyclohexene or hexane. But if it has alternating single and double bonds, this actually is what they call an aromatic. So you see that one on your list as well. So those ones I think I have on your little handout. They're in the upper right-hand corner. So this is where you have 6 carbons in a ring, but they're alternating single and double bonds. This actually makes a very stable molecule. So remember that each of those corners, you might see it drawn like this. You might also see it drawn with the ring, with the double bonds in the opposite sides. It's fine, it's just every other. I've also seen it drawn like this. So just know those are all exactly the same. I'll try not to draw it with the circle, but sometimes they'll put it in books and like not describe it. But really this is very stable because it's really like each of those bonds acts like it's 1.5 bonds. So alkynes are super reactive with the triple bonds. Alkenes with the double bond are kind of reactive. Alkanes are usually pretty stable. So this one makes it kind of like a half and half. So it acts like it's 1.5 bonds. It makes it pretty stable. Otherwise, so they call it an aromatic. So we have alkanes, alkenes, alkynes, and then aromatics. Those are the ones that just have carbon and hydrogen. There's no other atoms found. So now, because it won't come back, so now, reconnect. Next one are the alcohol containing and the nitrogen containing groups. So these first 3, you have alcohols, aldehydes, carboxylic acids. So in alcohol, it's when you just have an OH group hanging off of a carbon. And there's nothing else on that carbon except hydrogen. So that's kind of an important thing, an important way to pick it out. So if you look at this, so this is ethanol. CH3, CH2, remember F is 2 carbons. So ethanol is an alcohol group on a 2-carbon group. So we're not really doing any of the naming things, but if you see a carbon that has hydrogen on it and an OH sticking off, that's an alcohol group. But if you see an aldehyde, so notice the way that the aldehyde is listed, and I'll actually give it to you as a structure, so I think it's a little easier to pick out. So see how it looks like the OH is backwards? So it looks like HO. So remember, in a condensed structural formula, the carbon, whatever's after the carbon, tells you what's around it. So this one tells me that I have a carbon with 3 hydrogens around it, right? Because it's CH3. And then CH2, this tells me that I have a carbon with 2 hydrogens around it. So this one tells me I have a CH, tells me that I have a carbon with a hydrogen attached. And then there's an O. Well, I know that carbon has to have 4 bonds. Do you see that right carbon only has 2 listed? Okay, so that's how I know this is a double bond. Because that makes it 4. Oxygen has to have its 2. So the alcohol group up here, this CH3, CH2, and then an OH. So that in the way that it's written actually kind of tells you the direction, but I'll show it to you in terms of structure. So an aldehyde is kind of unique because there's a double bond oxygen. It's always on the end of the molecule. And notice that the carbon it's attached to has nothing but hydrogen. If it's an alcohol, it'll be an OH hanging off a carbon that has nothing else, just hydrogen. But if I kind of do a combination of these two, if I do like an alcohol and an aldehyde and hook them to the same carbon, that's where I get a carboxylic acid. So if I look at CH3COOH, so CH3 just looks like a carbon with 3 hydrogens, right? Just from that condensed structure. Then I have a CO. So I know that I'm going to end up with a double bond oxygen and then an OH. So that still gives me those 4 bonds to each carbon, 2 bonds to each oxygen, 1 to each hydrogen. But do you see how it kind of looks like if I took an alcohol and an aldehyde and combined them? So the OH and the double bond oxygen are both off of the same carbon. That's a carboxylic acid. So an example of this, vinegar, is a carboxylic acid. That's what that is. CH3COOH is vinegar, acetic acid. The formaldehyde molecule that we looked at, that was an aldehyde. So can you see the difference between those 3? How an alcohol just has an OH hanging off of a carbon, and that carbon has nothing but hydrogens on it. The aldehyde has a double bond oxygen hanging off of the carbon, and otherwise there's nothing but hydrogens on that. But a carboxylic acid is always on an end, and it's going to have 2 oxygens. One of the oxygens will be a double bond, the other one will be an alcohol, an OH. Do you see those on your chart? Okay, so I gave you, and I'll give you this on the test. So this is not something you have to memorize. Really, the big thing is I want you to be familiar enough that you could look at this chart and pick them out. Okay, so when you look at the alcohol group, see where it's a C, just OH. When you look at the aldehyde group, see how it looks like it's on the end. So I have a C, C, double bond O with the H. Then going down, find the carboxylic acid, which is over on the right, and see how it is on an end, but it's a carbon with the double bond oxygen and an OH group on it as well. Mm-hmm.
At the very top,
Mm-hmm.
is that like O hyphen then H? Or is it together?
Well, and it would be an oxygen, so you mean this OH?
In the purple what you wrote.
Mm-hmm. So it would be this, right? So it would be a bond to oxygen, bond to hydrogen. Remember, oxygen has to have 2 bonds. Hydrogen only ever has 1. So can you see in that one how it's like from the carbon to the oxygen, then oxygen to the hydrogen? Okay? So that way oxygen has its 2 bonds. Same thing like down with the carboxylic acid right here. This would be like a dash H. Like if I was going to show the bonds out. So remember, oxygen's got to have 2 bonds. Okay, so those will be like what you see. Now, the only time you see nitrogen, nitrogen is either an amine or an amide. So if you see nitrogen, the first example, nitrogen is attached to carbon, but there's nothing else attached to that carbon but hydrogen. So you see in this one, so when you see an amine, the nitrogen, it might have 1 hydrogen, it could have 2 hydrogens, but it's attached to a carbon that only has hydrogens attached. So that's going to be like kind of one of the keys, is the carbon doesn't have an oxygen on it. If the carbon does have a double bonded oxygen, then instead of being an amine, they call it an amide. So the A words, those are the nitrogen groups. If it's just a nitrogen with no oxygen, it's an amine. But if you see a nitrogen with the double bond oxygen connected, that's an amide. So you see amides, they're in proteins. So those are the peptide bonds or the bonds in proteins. They're amide bonds. Amines are typically like kind of smelly. They're like NH3 is ammonia. So you know how strong ammonia smells. Well, nitrogen, just pure nitrogen molecules, they're usually kind of stinky. They're not usually like molecules that you like have hanging around because they're kind of like fishy smelling. They smell kind of rotten. All of those nitrogen smells. So urea is a nitrogen molecule, but then it'll like break down, and that's why baby diapers stink so much, is because of the nitrogen contained. But an amine is a nitrogen attached to a carbon that doesn't have an oxygen. The amide is going to be when you have a nitrogen attached to a carbon with an oxygen on it as well. You see how that one's like drawn out? Not my favorite way of having a condensed structural formula, because it looks like a carbon to an oxygen to a nitrogen, but in fact, this carbon has a double bond, this oxygen's a double bond sticking out to a nitrogen. So you kind of see the way that it's drawn in that one. So find those two, find the amine and the amide, kind of down in the lower right corner or lower left corner on your card.
The amide is usually found in the middle of the.
Yes. Amines can be in the middle or on an end, but the kicker with the amine is there's no nitrogen on any adjacent carbons. Okay? So any carbons the nitrogen is attached to does not have any oxygens on it. Okay? So notice how the amide, there's an oxygen attached to the carbon that it's attached to. So like here. So the nitrogen will always have a carbon with the double bond oxygen attached to it. Okay, and then the other ones. So the other three, these other three are just different combinations of oxygen. All three of these are always in the middle of the molecule. A ketone is if you just have a carbon with a double bond oxygen, but nothing else. Notice there's no nitrogen on either side, because if it was, it would be an amide. So a ketone, like acetone, nail polish remover, is a ketone. And it's got that double bond oxygen, and it's always going to be in the middle of a chain. But notice there's no nitrogen on either side of that carbon. Ethers, like the early anesthetics, so they used to use dimethyl ether. They used to like put it on a cloth and like put it up to your face, let you smell it, and it would knock you out. Okay, so that was like the early anesthetics. That's when the oxygen's part of the chain. It's not like sticking off of a carbon, it actually spans the chain. But if I took a ketone and an ether and put them together, do you see how that looks like an ester? Can you see that there's an oxygen spanning two carbons, but then there's also a double bond oxygen? So it's kind of like making that carboxylic acid, kind of like a combination of the two. And all three of these are going to be in the middle of a chain. So you're not going to see these all the way on an end because they all kind of like span carbons. So this one's in the middle of a chain. The top one's in the middle of the chain. You're going to see ethers in the middle of a chain. Whereas like aldehydes, alcohols, they're always on the end or sticking off. This one's one all by itself, like amines and amides are the only nitrogen ones. Thiols are whenever you see a sulfur. So it might be one sulfur, it could be two sulfur groups together. We're just going to call them all thiols. There's a lot of sulfur-containing amino acids in egg whites, and if you've ever boiled your egg way too long, when you break it open, the boiled egg, what color is the yolk? It gets that green look to it. That is because of the sulfur amino acids in the egg whites become solid and actually form like that green ring. And then how do they smell? Have you ever had like a boiled egg that's like, that doesn't have that green ring? Like if you cook it till it's just done, it doesn't smell very eggy. But if you like way over boil it, that's when it gets that kind of like sulfur swampy smell. People all move away from you when you open your sandwich. It used to happen when I was in school because like we never got school lunch. We always like packed lunch. Sometimes my father would make us egg salad. People would be like, what are you eating? Like I get stinky face. That is because eggs will get that smell. So if you just boil them so they don't have that green ring, they won't have that quite that strong egg smell to them. It's just a suggestion. But that's because the sulfur groups typically have that swampy, stinky sulfur smell to them. Anytime you see an S, okay, you know it's a thiol.
Kind of like the sulfur medicine.
Huh? Well, those are sulfa. So most sulfa meds, so those are different than sulfur. So that's SULFA, like sulfathiazone. Okay. So different types of sulfur. They do have sulfur groups in them. Yeah, I'm like allergic to sulfa meds. I can't take them. Can't take any sulfa antibiotics, but it's not sulfur. They do have sulfur groups, but it is called a sulfa antibiotic. Then the last one. So the last one you see all the way down in the very bottom right on your sheet, those are phenols. Okay? So a phenol looks like an aromatic, and an alcohol had a baby. Okay? So the aromatic is that ring, the 6-membered ring with the alternating single and double bonds, but there's an OH connected. So if you see just this, always, when you see the 6-membered ring, check all sides, look for an OH. If there's no OHs, it's an aromatic. If there's an OH anywhere on the ring, now it's a phenol. So like Lysol is a phenol. Phenols were some of the earliest disinfectants that were used. In fact, phenol was used in the surgical setting. They realized, after many, many people died, they realized that things like hand washing actually reduced hospital-acquired infections, surgical infections. And so then they used to have doctors actually dip their hands in phenol and then do surgery, and found that they had a lot less they called it like child bed fevers that mothers used to get. And it was because the doctor would go deliver this baby, deliver this baby, deliver this baby, and not wash their hands in between. So if one mother had an infection, then the next one was going to get it. And so they found there was all these issues. So then they found, well, there are some chemicals that seem to like clean your hands. Okay, soap was one of them, but they found an easy, quick one was just to dip your hands in phenol a couple of times. The problem is it's Lysol, like it was strong Lysol, so it would cause your hands to be really red and irritated. So they found also they would take and mist this, so if they were doing surgery, and so they cut the patient open, and so that right there would be an automatic issue because they didn't understand about the whole iodine, betadine scrubs then. But they found if they had somebody in the operating room that would actually mist or spray phenol into the air, that it reduces any type of infections. So that was like very early on in this understanding about aseptic technique, trying to reduce transmission of infection. So phenol was one of the very earliest sort of aseptic or disinfectants that were used, but it's really much better on non-living surfaces. If you put that on living surfaces, it causes a lot of irritation. So a disinfectant you use on non-living things. Antiseptics you can use on living tissues. So that's sort of the difference in the chemical because of the strength, because of what the effects can be when living tissues come in contact with these. So it's good to kill bacteria, but it kind of irritates living tissues as well. All right, so let's look at a few. So there's aspirin, Tylenol, Advil, and Valium. Okay, so some different types of medications. So in looking at them, so look at aspirin first. In this upper corner, you tell me what functional groups do you see. So use your card, look at the functional group card. Look at their shapes. What is one thing that you see? Okay, aspirin does have the alcohol, but look at the carbon that's attached to the alcohol. What else does it have? Yes. Do you see that it's got a double bond oxygen? So if you see an OH, you're right, like it's an alcohol group, but always look at the carbon that it's connected to. Do you see that it has this? So that as a group is a carboxylic acid. Okay, so look, what else do you see? You see an aromatic, right? So here's the 6-membered ring, alternating single and double bonds. It's the 6-membered ring. So then you look to see, is there an OH on any of it? No. So that means this is an aromatic. Okay, one more. Yes, an ester. Yep. So that's it, because the other thing is just a CH3, it's just a methyl group, all right? So now look over at Tylenol. So what does Tylenol have? It has the aromatic, but remember to check and see if it's an aromatic or a phenol. What do you look for? Right, do you see that? So you see the aromatic, but see the OH? This makes this a phenol. What else do you see? So that OH can be on any corner of the aromatic, and it's still a phenol. It's an amide, right? So as soon as you see the nitrogen, you know that it's either an amine or an amide. Because that's all it can be. So nitrogens are going to be an amine or an amide. So what you do is look at the carbons attached to that nitrogen. Look to see, are there any double bond oxygens? If there is, it's an amide. If there isn't, it's just an amine. Okay? So since I see this, it's an amide. Okay? Go down and look at Advil, ibuprofen. What has it got? So it has the aromatic. Because you look at the corners, there's no OH, so you know it's an aromatic versus a phenol. There's one other. It's got a carboxylic acid. So car, then box, and then ilic is its name. So you see it here? So that's a carboxylic acid. All right, look over at saccharin. What does saccharin have? So what's that? A thiol. Thiol. Anytime it's got a sulfur. Doesn't matter what oxygens are attached or anything else. If you see a sulfur, it's a thiol. Two others. An amide. Yep. So see the carbon next. So you see the nitrogen. As soon as you see the nitrogen, look and see what the carbons next to it have. That one has a double bond oxygen. So this is an amide. And then one more. Aromatic. Right? So do you see the 6-membered ring? It's kind of weird looking, but do you see it's a double bond, single bond, double bond, single bond going around? So that's an aromatic. Now Valium. What does Valium have? It has an aromatic. It actually has two of them. Do you see that? They're both aromatics, 6-membered, alternating single and double bonds. No OHs on them, so they're not phenol. So that's, you can tell it's either an aromatic or a phenol. If you see that 6-membered ring with the alternating single and double bonds. Do you see another one? Which one? The upper or the lower nitrogen? Do you see there's two nitrogens? So I know the nitrogens are either amines or amides. They're going to be one or the other. So if you look at this one, you look at the carbons next to it, you're looking to see, do any of the carbons attached to that one have a double bond? Yes or no? So this one, do you see that? Right? So that nitrogen actually has 3 carbons attached, one above, one part of the ring, and then one, remember in a skeletal structure where you come to a corner, that's a carbon, right? So remember that's a carbon because it's a skeletal structure. So that one has a double bond, so that makes this the amide. But now see this one. Do the carbons next to them or attached to that nitrogen have anything? Not directly, no. So this is an amine. Okay, so what I did is, this is not a real molecule. I just made this one up, but this one actually has 9 functional groups. So take a minute and see how many of them you can find. If you didn't print out your PowerPoints, that's okay. Just see it, like you don't have time to draw all of them, but you can go back and look at this. So this one's in the regular PowerPoint, then it'll also be in the marked up one with them labeled. This one actually has 9 functional groups. So see how many of them you can actually find. Okay, tell me one. Just pick one. Tell me where about it is. Okay, and where do you see that? Bottom left? Okay, so this one's aromatic. Okay, what's another one? And where's that one? So do you see this one? All right, anybody else? Where? So you see one that looks like an alcohol where? Oh, well, see, so if it's part of a phenol, then it's not going to be an alcohol. So she was asking about the one sticking off. But if it's part of a phenol, then that's that whole group. So we wouldn't split it. So you wouldn't say it's an aromatic alcohol. You would say it's a phenol together. Okay? Okay. So coming down here, yes. So here's the nitrogen. So when you find a nitrogen, just look at any carbons connected to it. You're looking to see if there's a double bond oxygen. So yes, this one has it, so it's an amide. But which one? So this is a thiol. Where? Yep, coming down. See, this nitrogen just is attached to a carbon, so this is an amine. So there's no double bond oxygen on that carbon, so see the difference. This is where you're looking over here. If you see that nitrogen and you see a carbon with the double bond oxygen, that's an amide. Without it, it's just an amine. All right, so there's 4 more, right? So we got 5. Where? Yeah, very good. Yeah, that's one that sometimes throws people. Remember I said ketones? Notice that carbon's just attached to carbons. So it's just a carbon with the double bond oxygen in the middle of a chain. So this is a ketone. Yeah, so where's an ester? To the left of it. Did everybody get this one? All right, so there's a carbon double bond oxygen, but there's an oxygen with it. Okay? So if it's in the middle of a chain and you see an oxygen span with a double bond oxygen on one of those carbons, that's an ester. 2 more. Which one? The upper or the lower? The lower one? So this one's always going to be on an end. This is a carboxylic acid. It'll always be if you see a carbon with a double bond oxygen and an OH on the end. So that leads us to the last one. What's that one? It is. It's an aldehyde. That is when you have a carbon with the double bond oxygen and just a hydrogen on the end. Okay, so make any of the ones that you didn't see. And notice all the rest of them, nothing but carbon, single bond carbon groups, right? CH2s, CH3s. So you're really, when you look at a molecule, first thing I always look for is nitrogens, because then I know that's an amine or an amide. Then I look for the ring structures with the alternating single bonds. Then I know that's an aromatic, or if there's an alcohol, it's a phenol. If you see a sulfur, you know it's a thiol, okay? So like pick those ones out first. Now then the other ones, the ones where there's oxygen, there's a lot of different combinations, but if you find an oxygen, you're like, is it on the end? If it's on the end, it could be an aldehyde or it could be a carboxylic acid. Is it in the middle? If it's in the middle, it could be a ketone or it could be an ester. So that kind of to help like differentiate those. Really, alcohols could be anywhere. They could be in the middle. It could be on an end. They're not like defined. So here's another one. So this one has like, I built this one with the mastering chemistry, like the chem draw. So if you had a challenge doing any of the chem draws, I don't know if you did or not, where you had to build a molecule, The key with these is you always put down the atoms first. You put all the atoms down on the little, like the little palette that they have. So you pick carbons, you put the carbons down where you want. You pick hydrogens, you put them down. You put the oxygens down. Then you link them together. So if you try to do each atom and link them together, it just starts randomly putting like things all over everywhere. It's very frustrating. But the kicker is always put down the atoms first where you want them to be. So like carbon, 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 change over hydrogen, 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 hydrogen. Put them where you want on like the chem draw board. If you have to put an oxygen, you put an oxygen. Then go to the little line where you do the bonds. And when you do bonds, if you click like over on the left side of the little palette, there's like a single line, a double line, a triple line. So click the single line. Then when you hover over a carbon, you click and drag to the bond one you want to link it to, and that'll form a single bond. Okay, so like when you hover over it, it like turns light blue. Then you click and drag to link those two atoms together, and then link the next ones together, and then that's how you can like form the bonds. Okay, so looking at this one, what's one you see? You see the thiol straight away. See, look, there's a sulfur. It's a thiol. Move on. Right, because that's the only thing it can be. Do you see something else? Where? The ring with the OH, right? So if you see the ring, it's going to be an aromatic or a phenol. See that one? Got an alcohol. It's got an OH on it, so I know that that's a phenol. And then there's two aromatics. Good. So this one's an aromatic because I just see the six-membered ring. And then this one's an aromatic, six-membered ring all the way around. All right, what else do you see? Where? Yeah, here. So you see the nitrogen, it's connected to a carbon that's got a double bond. So that is an amide. Yep, and between the two aromatics, see this nitrogen's connected to a carbon and an oxygen, but there's no double bond oxygen, so this is an amine. So now this, so what would that be? An oxygen in the chain. Just an huh? Yeah, it's an ether. Yep, the oxygen, if it's just in a chain, no double bond oxygens near it, then that's an ether. I see one more. It's not a ketone because it would be in the middle of the chain. So that double bond oxygen would like need to be like right here. It's an aldehyde because aldehydes are always on the end. Good. All right. So there's one more. I'm going to skip that one and we'll practice that one first thing next time. Okay? So going through the next whole section, it's all about what they call isomers. So isomers, remember, are where you have the same number of atoms, but they may look different, or they may actually be put together differently. They may have different bonding arrangements. And so the term isomer, iso means same. Okay? So like isotonic is like the same salt, so that means like balanced or equal. So iso means the same. So it's really based on the way they look and the way they're put together. So the first two are if you have what are known as structural isomers or conformational isomers. So this first one here, where you took C4H10, we actually did this in lab. So C4H10, 4 carbons, 10 hydrogens. I could put them all in a chain, and what is that called? 4 carbons in a row is butane. Okay? But then this one, the one next to it, see where it's 3 carbons in a row, but one's hanging off? So 3 carbons in a row is, gives the P, propane. And then this group hanging off is a CH3, so that is a methyl, and it's hanging off of carbon number 2, so that would be 2-methylpropane. So see how they have different names? When you look at them, do you see that they have different bonding arrangements? Those are structural isomers. Okay, same formula, different connections, and the big thing is the names are different. And that's really the kicker. Same number of atoms, so they have the same molecular formula, different connections, different bonding arrangements, different name, those are structural isomers. But you see the two that are over on the right? Do you see the first one is 4 carbons in a row? So that one is butane. But when I look at the one on the far right, how long is the longest carbon chain? There's 3 across, but you see there's one going up off of the end. So this, do you see that that's actually 4? So that's also butane. So remember they call it like the straight chain is the zigzag, but the bent chain is the one that looks more like a cup or a U. But they're both butane. But sometimes when you first look at them, you might say, oh, they're different because they look different. But if you name them both, they have the same name. That is what conformational isomers are. Same molecular formula, same name, they just are drawn differently. I could take this and I could have it go like this, right? So I could have CH3, CH2, CH2, CH3, like in a straight, like in a vertical, or I could like lay them out straight. I could even have them go like this, carbon to carbon to carbon with their hydrogens and make it look kind of like there's like a stair step. That's all still butane. Those are all still exactly the same, 4 carbons in a row with their 10 hydrogens attached. They just look different. So the trick to tell the difference between these two, 1, make sure they have the same number of atoms. 2, name them. If they have the same name, they're conformational isomers. If they have different names, then you know they're structural. So like with these. So if I have all 3 of these, this first one is what? 1, 2, 3, 4, 5 is pentane. 5 carbons, see here, 1, 2, 3, 4, 5 carbons as well. But it's not pentane, it's what? It's a butane. Do you see that the longest carbon chain is 4? And then this group hanging off is there's a methyl. And it's hanging off a carbon number what? 2. See, I would count from the left because that would be 2. So this is 2-methylbutane. Those two, those are structural isomers. Same number of carbons, put together differently, and they have different names. Even this last one, how many carbons do you see? There's 3, but there's one above and one below, so a total of 5. So it's just like pentane's got 5 carbons, but the longest carbon chain makes this a propane. This group coming up here is a methyl, and the group coming down is they're both methyls. So when we put them together, they're called dimethyl, and they're both on carbon number what of the propane? 1, 2, 3. So they'd be off of carbon 2. So all 3 of those would be considered structural isomers of a 5-carbon molecule because they all have C5H12. You should be able to count 12 hydrogens. If they're all single bonds, they're always going to end up having this as long as they're not a ring. So these are all structural isomers. Same number of atoms, different bonding arrangements, different names. But what if I look at the 2 at the bottom? So at the 2 at the bottom, how many carbons in the longest carbon chain? So it's a butane. Does everybody see that? Longest carbon chain is a butane. So this thing hanging off is a what? So it's a bromo. This one hanging off is a chloro. Now I got to do the numbering. Do I number from left to right or right to left, or does it matter? I would go from left to right because bromine's over on that end. So this is going to be carbon 1, carbon 2, carbon 3, carbon 4. All I'm doing is just numbering the carbons in the chain. So that means my bromine's a what? A 1, and my chlorine is a 3. and that's the lowest number combination. Otherwise, it'd be 2 and 4 if I numbered from the other direction. But then what if you number the other one? What's the longest carbon chain there? 4. Does everybody see? Oh, kicked me off again. Ah. So I'm looking at this one. I have 4, which means it's still a butane. I still have a chloro, because I have a chlorine hanging off, and I've also got a bromo. So when I go to number this, which way am I going to number? From that upper left or the bottom right? Bottom right, right? So this is 1, 2, 3, 4. So my chlorine is on carbon number 3, and my bromine is on number 1. So do you see they're the same? Both of them have 1 bromo. Both of them have 3 chloro. They're both butanes. So these are conformational. Sometimes they're easier to pick out. Sometimes you can just look at them and go, yeah, those are exactly the same. Sometimes you really do have to name them because it's hard. Hard to pick them apart. Okay, so we'll do one more. So looking at these. Questions you'll see is, are these structural isomers, conformational isomers, or are these not related? And the kicker to doing this is count the number of carbons. If they're all single bonds and no rings, they have to have the same number of carbons. So the first one has how many? Total. How many total? So this would be C what? C8. So this would be C8, age 18. Count the one at the bottom. How many? There's 8. So I have 1, 2, 3, 4, 5, 6 in a row, 1 above and 1 below. So if I see that they're the same, then I know they have to be related. Okay? Because it's going to be like one of the 3 answers. So if they have the same number of carbons, then I know they have to be related. So now the question is, are they the same molecule drawn differently, or are they 2 different molecules? They're the same but drawn differently. So if you find in the top one the longest carbon chain, do you see that it would be this one? 1, 2, 3, 4, 5, 6 makes this a hexane. Remember, that becomes the last name. These CH3s hanging off, these are both methyls. And they're on carbon what? You don't really have to write the whole thing out. You just have to figure out what they would be. 3 and 4. And if it wouldn't matter which way I numbered. Do you see that? They're both hanging off of 3 and 4. So this one would be 4 and this one would be 3. So then if I go down to the bottom and I do the exact same thing, longest carbon chain is a hexane as well. And then these are both 3-methyl and 4-methyl. So do you see that those 2 methyls are both off of carbon 3 and carbon 4? So that means these are conformational isomers. These are both methyls. We would hang them 1, 2, 3, 5, 6. So this one would be 4, this one would be 3. Doesn't matter which side you numbered from. They'd still be 3 and 4 or 4 and 3. See how those have the same names. So conformational isomers, same name.
It's like 3, 4 methyl.
I'd call it 3, 4 dimethyl, so that you put them both together, right? Remember, if you have 2, so if you had 3 chlorines, it's trichloro, 2 methyls, dimethyl. And that way you don't have to write methyl out more than once. You just list all the numbers in front that they belong to, they're hanging off of. Okay? All right, so do this last one. So this one, the one's up at the top. So first thing you do, count the number of carbons. So count the number of dots. How many dots do you see on the left? So I know it's C8. I know that there's a BR. How many on the right? 9. So if there is C9 and a BR, then I know that these two are not related. I don't have to name them. I don't have to go any further. They don't have the same number of atoms. Okay? They can't be isomers unless they have the same number of atoms. So just count the number of carbons first so that you don't waste time trying to go through and do the naming when you really don't have to. Okay? I'll leave. I don't know why there's a chlorine here. It's always been here. It's just a straight chlorine that was dropped on the page. I don't know what happened. But well, I'm going to leave that one. We'll do that one too. We'll do that other functional group and we'll do this one next time. Okay? Structural isomers are put together differently but have the same number of atoms, different names. Conformational isomers have the same number of atoms but the same name. They're just drawn differently. Then we have the rings. So rings don't have the ability to rotate. So you'll remember in lab, if you had 5 carbons in a chain, they make their little zigzag, and you can take and twist them. So single bonds have this free rotation. As soon as you form a bond into or a chain into a ring, now it doesn't have the ability to rotate freely. So that like locks groups hanging off of the chain, it locks them into place. So in this example, so this one is showing a cyclopentane, right? So that is a ring of 5, the cyclopentane. The first one is showing, and you can kind of see they're 3-dimensional. The first one is showing that there is a methyl group, a CH3, that looks like it's sticking forward, okay, or pointing up. See how this one looks like it's sticking up? So it kind of looks like the bonds go in that direction. This one looks like it's pointing down. So there they have the dash, 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 CH3. So if you have a wedge and a dash, remember that means like I would put the ring on the board flat. So there would be one sticking forward and one pointing backwards. They're on opposite sides. The one that's over on the right-hand side, see how they both look like they're both pointing down? So that is why they use the dash, dash, dash for both of them. They could also do it the same, but they could use the wedges for both of them. No matter how I took this ring and twisted it, I couldn't make one go up if it's pointing down. Like they're either both stuck on opposite sides or they're both on the same side. So if you see the wedge and the dash, you know that this is trans. And I always think of trans, like trans is going across. So they're going across or on opposite sides. Whereas if I see both wedges or both dashes, then I know that those are cis. And I always remember cis is on the same side. Okay? So if the hanging groups on a ring have 2 wedges or 2 dashes, then I know that the name in the very front of them needs to be cis. If I see a wedge and a dash in a ring structure hanging off of a ring, and it'll typically be a cyclopentane or a cyclohexane, then I know that I need to use trans because one's on pointing forward, one's sticking back. They're sort of on opposite sides of the ring. So they show it sort of like trying to think of it in terms of like if I laid the ring flat, what would this one on the left be? This would be trans. So do you see how like one would be sticking up, one would be sticking down? Whereas over here, this would be the cis. So all I do is just put this in the very beginning. I name it normal. So the ring makes this a cyclopentane. This one also a cyclopentane. This group hanging off, those are methyl groups, right? This group hanging off over here is also a methyl group. They're hanging off of adjacent carbons, so I would call this 1,2-dimethyl cyclopentane. Same thing with the one over on the right. They're exactly the same. It's 2 methyl groups hanging off of the adjacent carbon, so I would number them 1 and 2. But I have to put the cis or trans out in front. So this one I would put as trans 1,2-dimethylcyclopentane. The one over on the other side, I would put a cis in front. So if you saw cis, you know that you're going to have 2 wedges or 2 dashes. If you see trans, you know that there's going to be one of each. And it doesn't matter which one. One of them makes sure there's a wedge. The other one needs the dash. Just to show that they're on opposite sides. You only see this with ring structures and with double bonds, but we don't name double bonds in here. So you're never going to have to name one that's got a double bond just because we don't work with those. But here's like what it would look like if you were thinking about a double bond. Have you ever heard the term trans in a food or a molecule before? Trans what? So have you heard of trans fats? Trans fats is definitely just like this. So notice how when trans you have, and it has to do with fats that have a double bond, trans fats are going to end up having a chain that creates this sort of like up and down arrangement. Normal fat molecules all exist like this. And so that you would call the cis double bond arrangement. So we'll talk in the next chapter a little bit about fatty acids, about fats versus oils, and then how you can take oils, which have double bonds, and convert them into saturated or single bond fat molecules, like when you make margarine or if you make Crisco. Those things all start as an oil, but they get solidified because of a chemical reaction they do, which is called hydrogenation. So that's in the next chapter. But that's where cis and trans, the reason to kind of pull this in is because we're going to talk about it a little bit from a nutritional standpoint. Okay? I'm not going to talk about, I actually took all these slides and just moved them into chapter 5, just because your book splits these two, I don't know why, but they split the discussion about lipids into 2 chapters. I'd rather just cover it in 1 chapter instead of covering half now and half later. So we will actually cover this in chapter 5 in total. So there's none of this. We'll talk about all of this in the next one. So this just brings us to the last topic. The last topic in this chapter talks about molecules that have a special grouping of carbon. Those they call chiral. So I know it looks like chiral, and I'm fine if you want to call it that because it does look like chiral, looks like kind of like chair, like the way it's said. But they're chiral. Carbons are a special kind of carbon. These are carbons that have to have 4 single bonds. I don't know why my pen's acting all wonky now. Now it's like way too sensitive. It's a carbon that has 4 single bonds, and all of those bonds have to be something different. Okay, so the groups connected to a carbon with 4 single bonds are all different. So just in this example, there's a carbon. On one side, there's a hydrogen. Another side, there's a chlorine attached, then a bromine attached, and then a CH3 or a methyl group attached. So that carbon now has 4 different groups. If I make the mirror image of this molecule, they're not identical. They're mirror images, but they don't sit one on top of the other. So here's an example of 2 molecules that have chiral carbons. So one of them is the smell or the aroma you associate with an orange, right? So like if you pick up an orange and smell it, that kind of citrusy, orangey smell, that is from a molecule called limonene. But there's 1 chiral carbon in this molecule. So I was looking for the 1 chiral carbon. It's that one, right in that very center at the bottom of the ring. But then if I took and make the mirror image of that, so notice like at the very bottom, the little group hanging off is a dash, 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 so it looks like it's pointing back. But look at the mirror image one, it would be pointing forward. So that is also a molecule called limonene. But instead of smelling like oranges, this smells like paint thinner, right? So turpentine is like a furniture polish or a paint thinner you use for like oil-based paint. Pretty different. One is really pleasant. The other one's very sharp. Same molecule. The only difference is because they have one of those weird carbons, they have very different aromas to them and different properties. So in looking at them, By definition, a carbon is chiral if it has 4 single bonds, which means it always makes the tetrahedral, right? Remember, carbon with 4 single bonds has that tetrahedral sort of shape. But all the groups attached to that carbon have to be different. So in this one this is a hydrogen. I'll just draw them because it doesn't look like you can see them. There's an OH, that's the little blue section above. Below is a CH2CH3, and the green one over on the right side is a CH3. So now some students look at this and they go, well, there's a carbon below and a carbon to the right. Why isn't that the same? But what you have to remember is OH, that's a group. Hydrogen, that's a group. This whole thing below the carbon is a CH2CH3, and that is different from a CH3 that's to the right. So it's everything above, below, to the left and the right of the carbon with 4 single bonds. They all have to be different. That's how you know if something is chiral. So when you look at the one where they did the mirror image and laid them on top, do you see that the green and the white don't match up? Okay, and that's what happens with the chiral carbon. So now really, this is like I have a left-handed and a right-handed molecule. So I have 2 molecules that are not identical, even though they have the same formula and they have the same bonding arrangement. But because of that chiral carbon, they make what are called enantiomers. So this is really the last isomer. So conformational isomers, same molecule, just drawn differently, but they'll have the same name. Structural isomers are when molecules are put together differently and have different names, but same number of atoms. Stereoisomers are the cis and trans. So the stereoisomers are the ones that are put together differently but don't have free rotation. So things sticking off of a ring get stuck, pointing up and down, or both pointing up or both pointing down. This is the last one. So these isomers, they call them enantiomers because these make mirror images that are not identical. And they may have very different characteristics from each other, like the one that smells like paint thinner versus smells like an orange. Another one, like rye bread. Rye bread has those little seeds in it called caraway seeds. You know the smell of rye bread? Rye bread and spearmint, the chemicals that create the chemicals that create the odor of rye bread, the caraway seed chemical, and spearmint, the mint smell of spearmint. They are mirror images of each other. They smell really different. Like you're never going to smell a rye bread loaf and go, it smells minty. Not going to happen. So it's like your nose knows the difference between them. Your nose can identify the difference between things that are just mirror images of each other. And it's all because of that chiral carbon. So look at a couple of them here. So the rules, you can remember this. If a carbon has more than one hydrogen directly connected, it's never chiral, okay? So if a carbon has more than one hydrogen directly connected, it is not chiral. So what does that mean about that first molecule? Are any of those carbons chiral? No. Carbon on the left, 3 hydrogens. Carbons in the middle, 2 hydrogens. Carbons on the far right, 3 hydrogens. If you see more than one hydrogen, so if it's a CH2 or a CH3, you know they can't be chiral. It can't have but one hydrogen directly connected to it. Okay? So that's how I know that there's no chiral carbons. None. Because they all have more than one hydrogen attached. And it's always like directly attached to the carbon. The other thing, rule number 2, if a carbon has a double bond or a triple bond, not chiral. So both of the carbons, like if you have a carbon double bond carbon, both of those carbons you can throw out. They can't be chiral. So let's look at this one. So what Which ones can you throw out straight away? This is a sugar. This is a 5-carbon sugar. What about the top one? Why? Okay, so look at this first carbon. Can it be chiral? Why? 2 hydrogens. 2 hydrogens, not chiral. What about the second one? It's got a double bond, not chiral. Okay, so some of them are pretty easy. Just like look at the carbons. If you see more than one hydrogen directly connected, no. If you see any double bonds connected to the carbon, no. Okay, now what about this third one? On the left is a hydrogen, on the right is an alcohol, right? So we have an H and we have an OH. Those are different, yes? Okay, now above is a 2-carbon molecule with 2 oxygens and 3 hydrogens. Below is a 2-carbon molecule with 2 oxygens, but how many hydrogens? How many do you see total? There's 2 plus another one, so there's 5. So do you see that above and below those are different? Okay, above is a 2-carbon molecule with 2 oxygens and 3 hydrogens. Below is a 2-carbon group with 2 oxygens but 5 hydrogens. That one's chiral. So that carbon that I've circled, the one in the very center, this one is chiral. So you would put like a little star around it. That's a chiral carbon. So everything above, below, left, and right is really what you're like kind of like studying when you look at them. And those are the kind of ones that I'll give you. I'll like break them out so that it's easy to like see above, below, left, and right. What about the next one though? So there can be more than one chiral carbon in a molecule. So now we're going to look at the next one. So look at this carbon. To the left is an alcohol. To the right is a hydrogen. Below is a single carbon. Above is a 3-carbon group. Is that chiral? Are all groups different? All the 3 blue or 4 blue areas are all different? Yeah, sugars do this, okay? Sugars we're going to talk about in chapter 6. But you'll see there's a lot of chiral carbons in sugars. So you get a lot of these right and left-handed forms. So this is also chiral. What about the last one? What about the carbon at the very bottom? That last one. Can it be chiral? Why? It has 2 hydrogens, CH2. Once you see that, no. It's got 2 hydrogens. So that one actually has 2. So you would say that there's 2 chiral carbons here. So look at that top right one. Is the left carbon? Is this left carbon chiral? Why? 3 hydrogens, so no. Okay, what about the one over on the far right? No, because more than 1 hydrogen, right? So you see, if you see a CH3, if you see a carbon with 3 hydrogens or a carbon with 2 hydrogens, you know automatically you can throw them out. So now let's look at the one in the middle. So the one in the middle, above is an OH, below is an H. To the left is a CH3, to the right is a CH3. So can that be chiral? If to the left is a CH3 and to the right is a CH3, do you see that the left and the right are the same groups? So to the left, the entire thing to the left is a CH3. The entire thing to the right is a CH3, so that's not chiral. It has 2 CH3 groups. So it's got to have 4 different groups. What's above, below, left, and right have to all be different. The entire group has to be different. So this one, again, this has none. There's no chiral carbons in that molecule. The carbons on the end have 2 hydrogens or more than 2 hydrogens. The one that's in the middle actually has 2 CH3 groups, and so those are not different. So if I looked at the mirror images of these, I'd be able to lay them on top of each other. So there's the last one. So let's do the CH3, CH, CH, CH3. So what do you know about the end ones? Yeah, those ones are the easy ones, right? So this is a no, and this is a no. Because anytime you see CH2 or CH3, you know that can't be chiral. So now I just have to look at those middle ones. So what do you think? They look the same, but is this chiral? So what does this mean when you see CH? Remember, that means that this H is up here, right? And I wouldn't like draw it out this way. I need to change this one, like put the hydrogen above. So above is a hydrogen, to the left is a CH3, below is an OH, and to the right is a 2-carbon group. So are all those different? Yes. So all of those are different. Yes. I have an H, I have an OH, I have a CH3, and then I would have this whole group over on the right. A 2-carbon group with an alcohol over on the right. So that one's chiral. So then the last one. What about this one? And again, that CH would really be like an H sticking up. Is that one chiral? Hydrogen up, methyl to the right, alcohol below, and a 2-carbon group to the right. So that would also be. So you would actually say this one has 2 chiral carbons. Okay, I think I have, well, I have some, I'll do one or two more of those. So we'll do the functional group, one more practice, like there's one we didn't do. We'll also then do, what was the other one? Oh, I think I did an isomer one. Okay, so we'll do the isomers, the functional groups, the isomers, and then I'll do a couple more of these ones just to practice, like, and it won't be like a huge molecule. It'll be like a molecule, all single bonds. It won't have a whole bunch of functional groups because that'll make them complicated. But we'll finish up this chapter, the last topic in this, with chirality. It's like, well, why is this important? Because this all kind of relates to drug chemistry. So it relates to medications and the importance. I did make a couple of changes to those, to some of the molecules on there, but I'll just show them. I'll show them to you next week. Okay. But you can pretty much finish, like start working on those chapter 4, the post-lecture ones, the ones that we missed. I'll leave chapter 4 open, so I don't know if you heard that. So all I did was take the first 6 questions of chapter 4 and use that on exam 2, because there were 12 questions in chapter 4 we hadn't talked about in the post-lecture. So make sure that you go back and do the last, so it'll be like questions 7 through 18. Those are the last 12 questions in the post-lecture, and those ones you should pretty much be able to answer now. You also have 2 dynamic study modules. One's on isomers, which we just talked about, and the other one's on chiral molecules. So that should help with recognizing and identifying the chiral molecules too. So get those done this weekend, and then we'll pick up there. Finish the last bit, take maybe 15,